All right. Hello, everyone. Welcome to another Quantum Matter seminar. Today is my pleasure to give you Cheng Peng from Slack, who's going to be talking about two-dimensional magnets, van der Waals magnets. Please, Cheng, take it away. Thank you.
Thank you, Andrew. Thank you so much for inviting me to this quantum material seminar. And it is my great pleasure to give a presentation about my most recent interest on the van der Waals magnets. So let's start. I recently searched a lot of papers on the 2D materials, and it has become a very hot topic in this area that van der Waals magnets MPX₃ has become the new star. And people has already made many measurements on those materials, and they all show very interesting behaviors. So there are many proposals, for example, like to do the 2D engineering of those materials for the application in the electronics and more applications in making devices. Just a very brief overview of this material. As you can see here, that this materials contains a family of materials. For example, the transition metal side, it can be replaced by either magnesium, iron, copper, or nickel items. And in combination with the other side, such as sulfur, selenium, and tellurium. So either you could make a combination for a pure compound, or people could also dope this material with different transition metal ions, and also from the sulfur, selenium, and the tellurium sides. So this family contains many members, and they all have the same structure. I show a brief lattice structure here. For example, an MPX₃, it has a van der Waals layered structure. So each layer, it contains the hexagonal structure made by the transition metal size, and also interlayer are separated by the van der Waals gap. However, even though the layer system are pretty well defined, there's still weak strong coupling between each layers. I will talk about that later. So from the experimental side, you can see like this is an example under the microscope of the MPX₃. So you could see pretty clear the layered structure, and this material is relatively easy to be exfoliated to monolayer and thin film structures. However, some of the material is very stabilized in air, but some are not. For example, COPS₃ is very difficult to grow and not easy to handle. And also for nickel, sulfur, selenium, it's very difficult to grow a single crystal like this. So normally people would try a lot of other methods, but only could get a mixed compound. But no matter how difficult that can grow, that people have tried many methods, and most materials in this family would be pretty stabilized in air and could measure either in the X-ray or neutron diffraction measurement. So there are many good techniques that can characterize this family of material. You may already see many times from literature or talks about this figure, why people are so interested in 2D materials, because they have many applications and also it's relatively easy to characterize. And from the theoretical perspective, modeling those materials would also be a very interesting topics. For example, the magnetic behavior could be modeled by spin model, such as Ising type model, XY model, or Heisenberg model. For example, if we look at the magnetic behavior, it's pretty much similar as the iron phosphorus trisulfide could be described by the Ising model. And some other compounds like magnesium, cobalt, and nickel, they behave either as an XY or Heisenberg model, or some other cases, people also propose many other models to describe different behaviors of the system. However, as I will talk later, that modeling those materials has some arbitraries, so that people taking carefully about what behaviors we want to model. And in the 2D material system, people could do many other techniques such as a moire pattern or making devices. That makes this family of material very interesting to the applicational side. So as talking about modeling such van der Waals material, there are a few key aspects we have to consider in our mind. First of all, this system, there are isostructure antiferromagnetic compounds, as many previous study has reported, such as the Curie-Weiss temperature and antiferromagnetic structure of the system at low temperature, and also like susceptibility. It uncovers the antiferromagnetic behavior of those compounds. However, even though the antiferromagnetic behavior are dominant, there are still some other problems we need to consider each of those family members. For example, some antiferromagnetic behavior it later uncovered to be a zigzag order, some could be a Neal order, and some other along the A-axis, but some magnetic order along the C-axis, which is perpendicular to the AB plane. The second point that we have to consider in our mind is the space group. For example, all the family members, as I mentioned before, that they all belongs to the hexagonal structure. However, if we measure the neutron diffraction, when we want to look for the magnetic peak or the magnetic, to identify the magnetic structure, we need to consider the magnetic the vector for the system. I showed a figure on right-hand side. This is a neutron diffraction measurement. The right arrows are pointing out the forbidden structures of the C2M space group. However, they are appearing because the system has a zigzag order, as I shown in this figure. However, there are also some other peaks which is not the 010 magnetic peak, but still showing in the diffraction pattern like this one. This is because the system has a 120-degree rotation in each domain. Because when grow your sample, the sample may contains different domains, and each domain they have a 120-degree rotation because this is a hexagonal structure. So some of the peaks which is associated to the magnetic peak of 010, but showing up in some particular case space. So that after analyzing those peaks, we could get an idea about what kind of magnetic order that the system may have. So the magnetic behavior are mainly contributed by the transition metal ions, which form the hexagonal structure or the honeycomb lattice within each layer. So that when we model this system, we need to consider what spin momentum each transition metal atom might have. For example, the magnesium, iron, cobalt, and nickel, they have the spin momentum from 5½ to spin 1 system. So I will take the nickel MPX₃ material as an example to discuss more details about how to model this spin model for understanding the magnetic behaviors of the system. All right, so how to do it? How to model the spin behaviors? So right now, people have many material methods about doing this. I show one example, but I'm sure there are more methods that we could try for modeling the magnetic behaviors. Here, this photo shows the neutron measurement of the MPX₃ single crystal. So from here, you can see the magnon spectrum at some wave vectors, and it's relatively easy to model this behavior in linear spin wave, as the magnon behavior are contributed by a spin 1 model. However, when you do this, you have to know, or you have an idea in your mind which spin model you want to use. For example, MPX₃, because the system has a hexagonal structure, so people could make a spin 1 model on honeycomb lattice, and each nearest neighbor, next nearest neighbor, and third nearest neighbor electrons, they could have an electron exchange, so that the spin interactions might happen between the first, second, and third nearest neighbor nucleosides. And also some other interactions, such as the single ion anisotropy, might appear because the system has a lattice, has a magnetic structure shown here, like it has a very tiny C component outside the AB layer, so that single ion anisotropy might appear to suppress the out of layer spin momentum. After you have such an initial guess of the spin system, then people could play with the linear spin wave softwares and get an initial guess for the coefficients of each item in the Hamiltonian. However, sometimes this kind of method would be working pretty well, but sometimes it doesn't. The main reason is that there could be some freedom for choosing what spin interaction or what coefficient you want to simulate the magnon behavior. For example, I shown a result that come from this paper that they have tried many different coefficients, and eventually they decide this coefficient could be the best suitable combination for modeling the behaviors of MPX₃. However, we still do not know if this is a final answer. So people would also try other methods like first principle calculations or the perturbation theory to get a better idea about what kind of microscopic mechanism will give you such behavior of spin interactions. So how to choose a good guess for a spin model? You don't want to try as many as possible Hamiltonians because there are infinite large possibilities that you can try. Most of the time, we would have an idea about what kind of interaction are most likely to reveal the magnetic behaviors in your system.
However, there are still some uncertainties. I take one example from this paper. So this is a same Hamiltonian for an MPX₃, but it looks slightly different from the previous one. However, when people put either antiferromagnetic interaction or ferromagnetic interaction for the nearest neighbor nickel-nickel spin interactions, it sort of generate a very similar Magnon spectrum. So this is an impression that we get from this paper that maybe only using linear spin wave to fit a neutron spectrum may not be sufficient to give you a good guess or a final answer for the spin model of your system. However, in another case, people also propose a new model, such as XXZ model, to describe the behavior of a Raman result. So this is their model, and you could see like even though most of the items are pretty similar, however, the anisotropy in real space are included. So they claim that this model could be a better suitable case for describing the Raman to Magnon scattering result. This gives us a sense that maybe there's some arbitrary choice for your spin system. However, we don't like it, but this is the real world. In some even severe cases, like I choose one example from another van der Waals material, chromium triiodide, this problem would be more severe. For example, they have built a pretty complicated model to describe the magnetic behavior in chromium triiodide and its sibling. So there are more interactions in your system. And from the common sense that the more parameters you have, that the more likely that you could simulate and you could fit anything that you want. So people have tried either Kitaev model or spin model plus DMI interaction. They almost generate exactly the same spin spectral function, which repeat pretty well the neutron scattering measurement. So the two cases also tells us that if we only consider the linear spin wave fitting of the neutron scattering measurement, it's very challenging to distinguish the spin interaction. However, they still give us very important impression about what spin interaction or what Hamiltonian we could use as a good initial starting point. However, if we want to determine a more accurate spin interaction of your system, then we have to do something else by using other methods to get a better guessing of what spin interaction would be more likely to describe the real physics of your system. But there are still many debates remains for the same material, the same compound. So it's better way for us to dive slightly deeper into the microscopic mechanism of the spin interactions and to try to understand how to exclude or include more spin interactions to give a better description of experimental behaviors. Here I put an example also for an MPX₃. If you look at the lattice structure more carefully, as I shown in this figure, this is a single layer structure. The transition metal ions, they form almost a perfect honeycomb lattice without any strain or pressure. However, sometimes when people do a shear or other kind of strain engineering of the material, then the honeycomb structure would be destroyed. So that gives us sense that the spin behaviors were pretty much determined by the bond length, bond angle, and how those electrons hopping between the atoms that all may contribute to the spin interactions. And also for this system, the transition metal ions are sitting in the middle of an octahedral crystal structure. So the octahedral structure will split the 5 degenerate d orbitals to 2 higher Eg orbitals and 3 lower T2G orbitals. So as you remember, as I mentioned earlier, that each transition metal ions, they carry different spin momentum. For nickel, the T2G orbitals are fully occupied, which means they most likely will not contribute to the spin interactions or the electron hoppings between the nearest neighbor or second, third nearest neighbor transition metal size. However, the Eg orbitals are half-filled. Then the spin says the total spin of each nickel will become spin 1 because the 2 half-filled Eg orbitals will have a pair. And when we think about how those electrons on each side will talk to each other, you have to consider the d orbitals orientation. This is very important for this family of material because each nearest neighbor electrons, each nearest neighbor atoms, they are not only directly connected through a connection within a layer. They also have a connection through the transition metal ligand transition metal side with the surface I painted as pink, yellow, and brown. They all out of layers, out of the AB layer. So the transition metal side would also have some interactions with the ligand side, but the hopping paths are not only within the AB layer. They sort of need to consider the d orbital's orientation so that which orbital would most likely overlap with the other orbital that may contribute to different spin behaviors. Seems that it is very complicated to fully understand all the possible behaviors, but most time we need to do an approximation which throw away the less dominant behaviors but contain the most important behaviors. Then we need to employ the DFT calculation for giving us a better understanding of which orbitals are more important to the other. And also, there are many tools we can use, such as TB2J or one-near downfolding to get the hopping integral estimated from the DFT band structure. So I show an example for one of our former work to estimate the spin interactions of an MPX₃. So 2 different methods, both are on top of fitting the band structure using the first principle method, and they all give a similar coupling constants, but quantitatively different values. However, the most important conclusion we get from the DFT simulation is that the J1, J2, J3 coupling, they sort of have different behavior, each either ferromagnetic or antiferromagnetic. However, my slides show some formatting error. This ferromagnetic interaction is J1 coupling. So the J1, it has a ferromagnetic between the nearest neighbor nickel size. However, J3 has an antiferromagnetic behavior. Then we need to ask why this system, it is an isotropic antiferromagnetic system. However, why the J1 and J3 have different spin coupling. So J1 is ferromagnetic, J3 is antiferromagnetic. If we go deep into the magnetic, the spin behavior that generated by the orbital overlapping, then the answer would be more clear. For example, I show the two possibilities between the nickel pairs on this side. The nearest neighbor coupling are introduced by either direct hopping between the nickel d orbitals or the indirect hopping between the nickel ligand and the nickel sites. So the first possibility, the direct hopping between the two nickels, either the EG, the dz square orbitals or the dx square minus y square orbitals, they all contributed to the direct hopping between the two nickel sites. However, for the indirect hopping, we need to consider the orbital, the orientation of the axis, and also the orbital, how they aligned with the x, y, and z axis in the system. So one possible hopping through the ligand would be the x square minus y square orbital through py. However, the on-site hopping also exists because the other connection is through px and the other the x square minus y square orbital. So there is a 4 steps processing of the electron hopping through the nearest neighbor nickel sites. And for the third nearest neighbor hopping, is more complicated because they are associated with 2 nickel sites and 2 ligand sites. So the nickel, the x square minus square orbital, it overlaps with 1 ligand py orbital and then hop to another ligand site, but px orbital, and then come to the second nickel site, the x square minus y square orbital. And such hopping will give you interaction between the third nearest neighbor nickel sites. And then if we do a perturbation theory that clearly show the interaction between the third nearest neighbor nickel sites are antiferromagnetic. However, for the ferromagnetic nearest neighbor interaction, both indirect and the direct hopping between the nickel sites should be considered at the same time. But the perturbation theory told us that the nearest neighbor interaction through direct hopping that only generate a ferromagnetic interaction, but the indirect hopping through the ligand p orbitals, this can give us a ferromagnetic interaction. So the competition between the direct hopping and the indirect hopping, and they are both contributing to the nearest neighbor spin interactions. However, the ligand mediated hopping survives eventually because the distance between the nearest neighbor sites is very difficult to have electron talking to each other. So this survive, this fail, then the eventual spin-spin interactions of the nearest neighbor side becomes a ferromagnetic. Then that explains why when we do the DFT simulation and then fit the J1, J2, J3 coupling, we see a ferromagnetic J1 and antiferromagnetic J3. However, even though using a DFT computation that sort of gives us a good answer, however, there are many examples like DFT also fails because DFT still have some intrinsic issues about carrying the spin calculation, because spin model calculations that requires a strong coupling, but DFT sometimes it doesn't handle that well in the strong coupling system. So another method we could use to double confirm whether the spin interaction that's simulated from either linear spin wave or DFT computation are reasonable, or if there are more spin interactions that we might neglect through the other two methods, then we could do another computation, which is a perturbation theory, to get another guessing about what kind of spin interactions should be reasonable to appear in your eventual spin system. So I put an example here, like the spin momentum of each nickel d orbitals. They somehow could be different along the different direction. This is because, as I mentioned, that the spin interaction between the nearest neighbor side, they are mediated through the ligand, the transition metal, ligand transition metal hopping. However, the plane of each hopping path, they are perpendicular along three different directions. And in each plane, for example, like this purple one, the d-square orbital is able to overlap with the p orbitals on the ligand side. However, along this side, even though the d-square orbital is able to overlap with the pz orbital in this plane, however, on the other side, if you consider the p orbital is overlapping with the dx squared minus y squared orbital, then the other path is broken because the d-square orbital is hard to overlap with any p orbitals in this plane. So we have to consider very carefully about, even though they are all nearest neighbor transition metal side, but they stay in a different environment, so that when we consider the spin interaction, maybe the three different nearest neighbor hopping terms should be considered, right? So that your eventual spin model would be different along three different directions. When we do this, there are many good examples that we can use to handle this system. But I will start from a simple example, like this one is a canary model for a single ion. So we need to start with an on-site Hamiltonian, for example, in this form, and then we should consider the hopping between each items, and then by treating them in the higher order perturbation theory, we could guess the energy that contributes by all the possible hopping paths. However, there are many different paths we should consider, because even the simplest nickel MPX₃ system, there are still two half-filled EG orbitals. So we either consider a ring hopping path from transition metal 1 to ligand 1 to transition metal item 2 to ligand 2 and come back, or they all happen at the same time. For example, the hopping from M1 to A1 to M2 happen at the same time with M2 to A2 to A1. So there are two cases for the single ion hopping, for the single electron hopping. However, the two electron hopping also happens at the same time. So if we consider all the possibilities, the perturbation method would be extremely complicated. However, it is still possible that we could use such method to double confirm the spin model that we get from the DFT computation. And also, either the perturbation theory will give you a better understanding of which interaction we should consider in the spin model, and also the perturbation theory would give us a more confident that even though we consider some very ambitious approximation in our system, then the spin model should still work for a simple system. And also what we could do after we have get this spin model, then one thing we could do is do the MRG computation to double confirm the magnetic order of your system. So for MPX₃, the magnetic order is zigzag order as measured in neutron measurement and also in X-ray diffraction measurement. So we could use the spin model to get a magnetic order. And then this magnetic order could also confirm that the magnetic order that computed from the spin model is correctly match the magnetic order that's seen in the experimental results. So that all those worked together will give us more confidence about, okay, this model works, this parameter works, and also this model we could use for computing more observables, particularly for predicting more behaviors that people would be interested to measure in their experiment. And another good thing that we have such a model is that when we see the X-ray diffraction from the real measurement, is also confirmed. It's also used to it could also be used to compute the magnetic transition and also compare with this X-ray measurement. So when extracting the coefficients from fitting the experimental data, then we get a value of this coefficient. Then when we use the same model and then compute the same behavior, and also it confirms that a Heisenberg behavior is more likely describe this system. So that may rule out some other model, for example, like XZ or XY model for describing the correct behavior of such system. So when we take them all together, then people will get a better understanding about, okay, maybe the behavior of the spin behavior of the system is not so arbitrary. We still can refine our model to be closer to the realistic world. However, that requires a lot of efforts, like we need to do experiment, we need to do a DFT simulation, and we even need to do analytical computations such as perturbation theory to compare, to make them comparing to each other, and then eventually have a good guessing about what material, what behavior, and what model we should use for describing those behaviors. Okay, so after we have spent so many efforts in modeling the system, then the other question is, can we try to predict more behaviors from this model study? Because from model, it's relatively easy to do engineering, but from the experimental side, it's very expensive and hard to get some setups done to measure a particular behavior. So people would always start from a model study to get a good guessing about what behavior or what physics could be the most interesting targets for the next experiment. If you remember that I mentioned slightly, the system of MPX₃ is very similar as another family of materials, which is a Kitaev material. The Kitaev material, I list 3 candidates of the Kitaev material. So they all have very similar layered structure as MPX₃ family of compounds. So probably they could have similar spin models for describe the spin behaviors of the system. However, if I slightly take one example of the Kitaev candidate materials, it shows that those spin interactions usually will have a strong spin orbital coupling to generate those Kitaev terms and also to generate the off-diagonal terms. Even though those off-diagonal terms are not favorable in the Kitaev materials candidate, but they all exist all the time because the system is not ideal. However, when we consider the strain or pressure of the system, more spin interactions might appear in your spin systems, but they are all very unlikely to maintain the system in the most interesting phase. So ideally, we will start from the system without any constraint. However, the constraint itself may also give us more spin interactions in your Hamiltonian, but that requires a lot more efforts to identify what constraint could generate which kind of spin interaction. Also, for the ideal hexagonal structure with cubic symmetry, if we consider the spin orbital coupling in the system, either from the transition metal side or from the ligand side, after doing all the derivation, we could see that the Kitaev spin interaction would emerge from a small portion of spin orbital coupling. So this is an example, like the spin orbital coupling is introduced on the ligand side, so that the final spin model will give you a finite Kitaev spin coefficients with the coefficients expanded proportionally to the lambda p square, and lambda p is the strength of your spin orbital coupling. Eventually, even though from the original system MPX₃, the spin model seems determined and without any spin orbital coupling on nickel, sulfur, and even phosphorus side. But if we do a doping on the system, for example, like replace the ligand from sulfur to selenium, then the system might dramatically emerge or find a Kitaev interaction along with all the other off-diagonal terms. So we also do the DFT computation to get an initial guess of the coefficients of each spin interaction. So you can see that the MPX₃ without any spin orbital coupling, the off-diagonal terms and also the Kitaev terms is almost zero. They're almost zero. However, when we manually increase the spin orbital coupling on the ligand side, then a finite off-diagonal term and also the Kitaev term, it emerges from the DFT simulation. So they all tells us that, okay, the spin behaviors are able to engineer by just simply chemical doping or replace some element from the same structure with the same lattice group symmetry. All right, so we want to say that even though there are many efforts have been paid to estimate the spin interaction of the material, but I'm sure this is a very big topic and also many other systems we could try. For example, today I only show MPX₃ and MPX₄. However, in this family, both replacing the transition metal set and also the ligand set will generate more interesting physics, but there are still many efforts we need to do to model all those family members of the system compounds. However, even though people have treat neutron X-ray measurement as an initial characterizing method of those materials, still other experiments may help us to identify more interesting physics of the system. Then sometime if we neglect some spin interactions in the Hamiltonian, that might be able to get an evidence from the experimental data, and then we could think about whether there should be more mechanisms that we need to consider in modeling the spin behaviors of the system. And also this methodology is not only applicable on MPX₃, it's also able to help with understanding ion pH3, magnesium, cobalt, and all the other behaviors. But right now, it's very challenging for considering the mixed compound because the mixed size might not very controllable in real system. So in the modeling side, right now we are only able to do the pure compound. But this is a very big area that how to treat the mixed compound reasonably. And also for future explorations, like a machine learning algorithm to predict a materials candidate, this system is also very promising because already it has shown a potential for different spin behaviors in your Hamiltonian. So when we train a machine learning model to predict a particular physics behavior or to predict a new structure that containing the same spin interaction, that all able to do as my impression gained from the literature study. But today I only talk about the spin model. I didn't talk about the other modeling strategy for rigs. So rigs, it has a very different modeling strategy, which is totally different from the neutron and the Rex measurement as I show in my talk. But I would like to do more explorations in the future for how to model the Riggs resonant spectroscopy. That may be another big topics in the future for van Waals mechanism and MPX₃. Or other materials in the system. All right. So this is the end of my talk. Thank you very much for my collaborators, and thank you all the good works that they have helped us for deepening the understanding of this material. So that is the end of my talk. Thank you for your attention, and I would like to take questions.
Thank you, Cheng, for a very nice talk, very nice work. The session is open for questions. Do we have any questions from the audience? All right, I've got a question. So in your calculation of the effective Hamiltonian, you seem to be using a basis of atomic orbitals, right?
Mhm.
So, if you use a basis of Vanier orbitals,
Yeah.
derived from the DFT,
Mhm.
you may find that there might be a strong contribution also from the phosphorus atoms. But here it's not taken into account. Uh,
Yes.
how do you think these results can change if you did?
Yeah, so this material is very likely that the phosphorus p orbitals almost doesn't contribute to modeling the spin behaviors. So even though I only show the nickel and the sulfur p orbitals here, but the density of states of the phosphorus p orbitals, they stays relatively deep and far away from the Fermi surface. So we may consider do the linear downfolding of this material. Usually we will choose an energy window close perspective that the spin interaction are mainly contributed by the hopping between those orbitals. So that I would like to say that the as long as the phosphorus p orbitals, their density of states and the electronic bands are stay pretty far from the Fermi surface, which means the electrons of the phosphorus size are really stabilized locally. So it's relatively safe to neglect the phosphorus p orbitals contribution and consider those electron orbitals near the Fermi surface within a finite energy window.
All right.
Mhm.
Thank you very much. Do you have any other questions? All right. If not, we thank Cheng one more time. Thank you, Cheng. And thank you, everyone, for joining us today. And I hope we see you again next week.
Yeah, thank you very much for the invitation, and this is a great pleasure.